Hi everyone, in this video we're going to be talking about complex numbers but in polar form or trig form. So sometimes you hear it as trigonometric form, but often you're going to hear more of the time polar form. So let's talk about the complex plane and vector representation first. So in the last video we talked about complex numbers, so if you need a review, go ahead and go back and watch that video where we discussed the complex numbers that involve I in it. So in order to graph a complex number, you actually want to change your coordinate plane, which we normally did x and y coordinate system. You change it to have I involved. So here's what I'm talking about. The horizontal axis is still a real axis and it represents x, but the vertical axis is now considered the imaginary axis. So what we used to call like the y-axis, we're now calling the imaginary axis. So honestly, that's the only new part to this in terms of graphing. So each complex number, a plus bi, so remember we talked about complex numbers, they have this form, real part plus imaginary part, and it determines a unique position vector. So we also talked about position vectors a couple of videos back. Before I show you the image, the position vector is a vector that starts at the origin, so its tail is at the origin, and then the head of the vector points to the point in space a comma b from this vector. And then initial point, like I just mentioned, is 0, 0. Terminal point is a comma b. So this is one example of a complex number graphed as a vector in the complex plane. So our x-axis is here. We can still call this our y-axis, but sometimes it's denoted with an I here, just to remind people that it's representing the imaginary number, so the imaginary axis. So you do it just like you do with regular rectangular coordinates. You're going to go 2 to the right for 2 positive real, and then down 3 for -3 imaginary. And then you plot this point. So it's not just a single point in space. This actually is a vector. So you just draw an arrow or vector from the origin to this point, 2, -3. Now the sum of two complex numbers can be represented by a vector. We talked about adding vectors in a couple videos back. The result when you add vectors is called a resultant vector, and we're just going to be adding two complex numbers. So this 4 plus I represents a complex number as a vector though, and then 1 plus 3i also a complex number, but also as a vector. So the two blue ones are your individual complex numbers represented as vectors, and then when you add them, you can use this parallelogram method where you draw a parallelogram involving the two vectors that you have, and then the diagonal through the parallelogram represents the resultant or the sum. And so you just add up the components. The real parts, 4 plus 1 is 5, and then the imaginary parts, 1i plus 3i is 4i. And then notice you can graph this vector by just going over 5 on the real axis and up 4 on the imaginary axis. Let's try this example. We're going to find the sum of these two vectors or two complex numbers and graph them. So before I do it, go ahead and try this out. Feel free to pause and just add these two vectors. Alright, so if you add them, you add up the real parts. 6 plus -4 is 2, and then the imaginary parts, -2i plus -3i gives you -5i. So we had done things like this in the past where we just added two complex numbers, but now let's represent this as a vector. So here's all three vectors. The original two, 6 minus 2i, -4 minus 3i, and then the resultant, the sum of those two. And so notice how you plot these vectors. You just basically find the point where they end at, where they terminate, and then draw a vector from the origin to that point. So 2 in the real direction, so 2 to the right for x, and then -5, so down 5 in the imaginary axis or y-axis. And then you just find where those two values meet. That's your point, and then your vector goes from the origin to that point. Now here is the relationships between x, y, r, and theta. Now what this is getting into, and this is going to come up again in the future if you are going to take, let's see, calculus, maybe the second level of calculus, you use polar coordinates. And so we'll discuss that in the next slide, but for now let me explain this relationship. So you're going to convert x and y, where we would normally graph a point x comma y, into points that involve r and theta. R and theta. So I can get to this point in space two ways now. So understand this process. You can, the same point in space, point P, if I leave my my laser pointer on P, I can represent that point two ways. I can get to this point by moving to the right x and up y, and then I land at P. However, I can also get to this point by knowing how much to sweep out for my angle theta. So I can start on my positive x-axis, and let me see if I can draw this process for you. So I can start on my positive x-axis, and I can just sweep out my angle theta. And then now that I know how far out to go for theta, if I also know r, my radius, once I stop for my angle, I start at the origin and just draw a straight vector, the distance r, whatever r is. Let's say r is 5. Then I draw this to be 5 units long, and then I land at P that way as well. So two ways to get to the same point in space. And why this matters and why this might be important, you might think, why do I need another way to represent a point in space? This is actually critical because this process allows you to not have to move in rectangles anymore. Instead of moving right and up and left and up and left and down and all that stuff, you can actually rotate. So this plays a big part in programming, and the idea of being able to rotate, like if you think of a video game, if you think of like old video games, the movements were more rectangular. You go up and over, up and over, up and over. And now you can rotate. You can rotate your view like circular, rotating, and then move forward and backwards. So that's this whole idea. So that's x and y. So here's how we come up with those two values, just so you know. It's from the trig you've been doing for a long time now. Cosine of this angle theta is just adjacent over hypotenuse. So if you solve this equation for x, you get x equals r cosine theta. Very much the same. You get y, if you solve this for y, because sine is opposite over hypotenuse, y equals r sine theta. And so this next part, these other two parts of this relationship between x, y, r, and theta, well, r equals square root x squared plus y squared, that's just your Pythagorean theorem. So we normally want just r, so we just square root your Pythagorean theorem. So this leg squared plus this leg squared gives me the hypotenuse squared. So you just square root this quantity, and that's r. And then the last piece of information is theta. So you want to find theta, and the way that you find theta is to use the relationship that tangent of your angle theta represents the opposite side over the adjacent side, excuse me. So you can always find theta using this relationship. The tangent of your angle theta is y over x. All right, so here's what I was saying. This is what we basically have just been talking about, polar form or trig form of a complex number. So a complex number, we've been using x plus yi, or we used a plus bi. The polar form of this exact same number is r equals cosine theta plus I sine theta. So let me just clarify what's happening here. We have a complex number that we've been using rectangular form for, x and y's. We are now representing that same exact number, that same exact point in space, with r and theta. It's that whole idea of rotating instead of moving in rectangles. So this is the same number, and here's why this is true. So x plus yi, we just talked about on the previous slide. X is r cosine theta. Y is r sine theta. So you times y by I, because y is the imaginary part of the number, imaginary component. And then all you do is factor out r from both of these terms, and that's how we get r cosine theta plus I sine theta. So this might look kind of funny, but this is just a complex number. This is a complex number in polar form. And now your expression, just so you're aware, some books, and sometimes when you see this, they're going to abbreviate the expression cosine theta plus I sine theta as CIS theta. So just be aware, it's the exact same thing. Cosine theta plus I sine theta is the same thing as CIS theta or cis theta. It's just a condensed way of writing it. So if you don't want to write this whole cosine theta plus I sine theta over and over again, you can shorten the way you write it. So then using this notation, r times cosine theta plus I sine theta can just be shortened as r cis theta. And then the last thing to note here, r represents the absolute value, or another word is modulus, of your complex number. Another way to talk about that is magnitude or length. If you are talking about a vector, r is just the length of it. It's like the hypotenuse in our picture a couple slides back. And then theta, we call that the argument of the complex number. So let's try out this example now that we've learned a little bit about polar or trigonometric form of a complex number. So this says express 2 times cosine 300 degrees plus I sine 300 degrees in rectangular form. So this is a number in complex polar form or trig form, and we're told to write it in rectangular form. So the rectangular form, as a reminder, is just x plus yi. This is how we learned about complex numbers. They were in this form. This is the new part, the polar or trig form. So we're converting. We're going back and forth. This time we're starting with polar, we're going to rectangular. So let's break this down. First, I would recommend that you distribute the number out front. This is actually your r value. So I just distribute it to 2 cosine 300 degrees and then plus 2 sine 300i. And then remember what we talked about. R cosine theta is x. So this quantity right here, this whole thing, 2 cosine 300 is x. And then r sine theta is y. So this whole quantity, 2 sine 300, equals y. So let's figure out what those values are. So looking at cosine 300, either using your unit circle or your calculator in degree mode, cosine 300 is 1/2. So then to find x, you just say r times that value. So for us, that's 2 times cosine 300. And so we get 2 times 1/2, which is just 1. So x, in our rectangular form of our number here, is just going to be 1. So we do the same thing for sine. So sine 300 degrees, using your calculator or unit circle, is negative square root 3 over 2. Y is r times that value. So for us, that's 2 times sine 300. And we get 2 times negative root 3 over 2, just giving us negative root 3. And then that's all we need to convert from polar or trig form to rectangular form. And so our number that we were given initially in polar is now 1 minus I square root 3 in rectangular. And so this has the format of rectangular numbers, and then x was 1, y was negative root 3, and then always times the y component by I. Okay. Now, as I mentioned before, this represents the same exact point in space, just 2 ways to locate it. The polar form uses rotating and a radius, so that you would sweep out an angle of 300 degrees from standard position and then move 2 units away from the origin. Or if you're in rectangular form, you move 1 unit in the real direction, or in the positive x, and then down square root 3 units in the imaginary direction, or y. So here's the image of that. So this is our point that we just found in rectangular form. Notice where it's at. It's located at 1 in the real direction and down root 3 in the imaginary direction. So just so you know, square root 3 is about 1.7. So this is about down here about 1.7. So now I'm going to switch the grid to polar form, polar grid, but the point's going to be in the same space. So I'm going to leave my laser pointer on top of my point, and now check this out. We're at the same exact point in space, but the way we get here is by starting at the positive x-axis and rotating an angle. We rotate around 300 degrees. So let me draw that out. So you start on the positive x-axis and you rotate around 300 degrees. Not a very nice rotation, but you see the idea. And then once you know where you're going to stop, you then go to the origin. Let me change my color here. Starting from the origin, you go out 2 units. So you have to measure 2. And so for us, they've already used grid lines for it. we go out 1, that's 1 unit, and then 2 units, and so we land at the same point. So that's the difference. It's just how we get there, how we travel to that point in space. Now we're going to convert the other way. We're going to convert from rectangular to trig form. This is actually a little bit more work. So what we just finished doing was going from trig or polar form to rectangular. And honestly, that way's faster. So this direction, I'm going to break it down into steps. So step 1, I would always start with the sketch. So sketch your rectangular form of your number, locate that point in your complex plane. Step 2, use the x and y values to find r. So we talked about this before. This relationship between x, y, and r is just x squared plus y squared. Square root that to get r. This was just from the Pythagorean theorem. And then the third step, you need theta. You always need an r and a theta if you're trying to get to trig form. So if we're trying to get to trig or polar form, we need r, which we get in step 2, and we need theta, which we're going to get in step 3 by using the fact that tangent of theta is y over x. So if we know y and we know x, we just divide, and we know tangent theta equals that value. So you can use tangent inverse. So just a caution, make sure you choose the correct quadrant for theta by referring to your sketch in part 1. So what I'm going to show you is to use tangent inverse to get theta, but that's going to give us only angles in quadrants 1 and 4. So if we happen to be dealing with a point in quadrants 2 and 3, we have to be careful about that. So I'll show you what I'm talking about with an example. Let's try this out. We're going to now convert from rectangular to trig or polar form. So write negative square root 3 plus I in trig form or polar form, and we're going to use radian measure. So let's first identify what we have going on. So step 1, the graph of negative square root 3 plus I in the complex plane, remembering that our rectangular form is x plus yi. This lets us know that x is the square root negative 3, and then the number in front of I represents y. So there's an invisible 1 in front of I, so y is positive 1. So then when we graph that point in space, or the actual vector ending at that point, we're going to go negative square root 3, so about negative 1.7 in the real direction, so to the left of the origin, and then up 1 in the imaginary direction, and we land at this point in space. So now we need to figure out, okay, well, how do I get to the same exact point in space by finding an angle and then a distance from the origin to this point? So we need r and we need theta. So step 2 is to find r using the fact that r is square root x squared plus y squared. So feel free to pause it and figure out what r is. Okay, if you plugged in x and y, you got that r is 2. So this distance from the origin to this point, or the length of this vector, is 2 units. And the last thing we need in order to go to trig form or polar form is theta. So step number 3 here, we're going to break this down and figure out theta. We know that tangent of theta is y over x, so we fill in our numbers. Y is 1, x was negative root 3. If you just rationalize this fraction, we have negative root 3 over 3. So now we need what angle theta gives us this tangent value. So we're going to use tangent inverse. So if you plug this into your calculator, or you just think about your unit circle, tangent inverse of negative root 3 over 3 is negative pi over 6. But from learning about inverse functions, tangent inverse is only defined in quadrants 1 and 4. So this would actually, this negative pi over 6, that's actually over here where my laser pointer's at, somewhere over here in quadrant 4. So I need to actually find out how to represent that value, but in quadrant 2. So think about how we can get that. This is a radian measure in quadrant 4. So before I show you, think about how could you change that to represent an angle in quadrant 2. Okay, so if you thought about it, hopefully you thought we should add pi. Or if you think of degrees, you add 180. You're basically going from quadrant 4 a whole straight line away, or 180 degrees, or pi away from there, giving you an angle in quadrant 2. So theta is 5 pi over 6. So you now found everything you need. We have r, we have theta, and so we just change our rectangular form of our number to trig form or polar form. So therefore, negative root 3 plus I is the same thing as, remembering that this is r cosine theta plus I sine theta, we get 2 times cosine 5 pi over 6. This should be a plus sign. Sorry about that. Plus I sine 5 pi over 6. Let me just fix this real quick. This is a plus sign. All right, and then you can use a condensed notation, 2 cis 5 pi over 6. So these are the same numbers, they just look different, they're just in 2 different forms. Let's try another one. So we're going to write negative 3i in trig or polar form. This time we're going to use degree measure. So step 1, let's sketch our graph of negative 3i in the complex plane by first identifying what x and y equal. So our rectangular form of our number is x plus yi. For us, that's going to be 0 minus 3i because we don't see a real part here. So the real part is actually 0. So x is 0. So x is 0, y is negative 3, and then when we plot that, we have this vector landing at 0, negative 3. So we didn't move left or right from the origin. That's the 0 for the real direction, but we just moved down 3 in the imaginary direction. All right, so now we have the point. Let's find r. So step 2, r is square root x squared plus y squared. So we just get 3. So now we know r is 3, and hopefully that value makes sense. R represents the distance from the origin. So if we're starting at the origin, we just travel down 1, 2, 3 units, and so we could tell by looking that r should be 3, but this is how we compute it algebraically. Then the third step is to find theta. So let's find our measure of angle theta, but be careful, this one's interesting, because if you use tangent theta, it's actually undefined, and that's because x is 0, so the tangent theta would be undefined, but that's still not that bad. It's not impossible to find what theta should be. You can tell just by looking on this one. This is one of your quadrantal angles. So before I tell you, think about if you can figure out what theta should be in degree measure. All right, so theta is 270 degrees. Hopefully that made sense. So 270 degrees is theta. You now have r, you now have theta, and you just fill that into your trig or polar form, and you get your final answer. So negative 3i is the same thing in polar or trig form as r, which was 3, times cosine your angle plus I sine of your angle. So cosine 270 plus I sine 270. Or you can condense it, 3 CIS or cis 270. And real quick, if you wanted to check, if you think about this, we can just check on our own really fast to see if you converted correctly. So cosine 270, I'm trying to get my pen out here. Cosine of 270 is 0 if you were to look at your unit circle or use your calculator. Sine of 270, again from your unit circle or your calculator, is negative 1. And so you have 3 times 0, so that's 0, plus 3 times I times negative 1, so that's just negative 3i. So that's a good way to check to see if you did this correct. All right, let's try this last example here. So write each complex number in its alternative form, meaning whatever form it starts in, write it in the other one. And then let's use your calculator to approximate some values if we need to. So notice part A is in trig or polar form. So that means we want to write this in rectangular form. We're going to go to the alternate form. 125 degrees, that's not one of our common angles that we know cosine and sine values of from your unit circle. So we are just going to use a calculator here. So in degree mode, type in cosine 125 and separately sine 125. And then you get this quantity. So 6 times these values. And don't forget when you're writing this out, the sine component, this has an I on it because this is the imaginary part. Then again in your calculator, you're just going to times each of these values by 6. So you're going to distribute this 6 and we end up with about negative 3.4 plus 4.9i. And that's our same number that we were starting with over here, 6 cosine 125 plus I sine 125. This is the same value in rectangular form. Okay, now let's try part B. And hopefully you remember from our last example, this one's going to be a little bit more work because we're going to trig form. We're going to polar form. So this is going to require our 3 steps. So step 1, let's sketch this complex number or the vector landing at this point. And so this is going to give us a vector in quadrant 4. It's 5 in the real direction and down 4 in the imaginary direction, and our vector landing at that point. Okay, so we are in quadrant 4, so let's find r. So using the fact that x squared plus y squared being square rooted is r, we get that r is square root 41. And then last, let's find theta. So using tangent of theta equals y, negative 4 over x, which is 5, and then tangent inverse. Okay, so theta is tangent inverse negative 4/5, which is going to give us negative 38.66 if you round, and this is from the calculator. Now, when you answer the questions like this and you want to go to polar form, you want your angle to be the positive angle. So even though this is technically my angle, negative 38.66, I want to change this to a positive angle. So just letting you know really fast, if you look at the drawing, this is my angle going clockwise. Okay, so that's negative 38.6 going clockwise. So I want the counterclockwise angle, the positive angle. So before I show you, think about how you would get that number. What would you do to negative 38.6 to get that value? All right, and hopefully you thought about adding 360. So we want to land at the same place. We want to land at the same vector, but we're going to go positive from here. So we just add 360 going all the way around our circle, and we get 321.34 degrees. We have everything we need, and so we just write our answer in trig form, polar form, and we get the following, that 5 minus 4i is the same thing as square root 41 CIS 321.34 degrees. And that's it.